Okay, so here's another polynomial that we're asked to factor down, and when you look at it, you can see right away that it's definitely not a trinomial because it doesn't have three terms in it, and it's not something that is going to yield to grouping because it doesn't have an even number of terms in it greater than or equal to 4. So some other kind of technique must apply here, and you can start off by looking it over and seeing if you can get a greatest common factor out of each term. But as you can see here, there is no greatest common factor. There's nothing you can get out meaningfully commonly from the coefficients. The first term doesn't have any y's or z's in it. The second term doesn't have any x's in it, so there's no common variable stuff you can take out of all the terms simultaneously. So this must be something else. It must be one of those, if it's factorable at all, one of those other binomial factorization setups, either a difference of squares or a sum or difference of cubes. So first off, as you're analyzing this, you can knock sum of cubes off right away, because as you can see here, this thing's not a sum, it's a difference. So given what we've got for our integer-based factoring setups, it looks like difference of squares or difference of cubes are the only two things that this could possibly be. So I guess to see what's going on with that, you can do any kind of combination that's convenient, looking at coefficients and powers of variables. Remember, variably speaking, perfect squares are variable powers that are multiples of 2, and again, variably speaking, perfect cubes are powers of variables that are multiples of 3. So when you look at this here, 6 might not immediately help you all that much, because 6 is both. It's a multiple of 2 and a multiple of 3. So x to the 6th is both a perfect square and a perfect cube. To know which one you're dealing with here, you have to actually look at some of the other variable powers that you've got going on here, the y to the 15th and z to the 3rd. And when you look at those, these are definitely not multiples of 2. 15 and 3 are in fact multiples of 3. So all of these powers, 6, 15, and 3 on the variable parts, are all multiples of 3. Therefore, it looks like this thing is going to be a difference of cubes. And in fact, that's true, because if you look at 125, 125 is a perfect cube, namely a 5. So we got a pretty good feeling here then that this thing is a difference of cubes. So why don't we just, although you certainly don't have to write this step, why don't we just note here officially what actually is being perfectly cubed to get you 125x to the 6th and y to the 15th z to the 3rd. So as we kind of noted here initially, 125 is the cube of 5, so 5 is being perfectly cubed to get 125. And then x to the 6th, well, when you think of how to deal with simplifications involving exponents, when you take power to power, you multiply exponents together. So that seems to imply then that the thing you cube to get x to the 6th is x squared. Since x squared cubed is power to power, you'd multiply those exponents together and get 6. Same deal now over here for the y to the 15th and z to the 3rd. Again, this is going to break down by a power-to-power setup, and you're looking for what you'd multiply 3 by to respectively get 15 and 3 for your powers on y and z. So the thing you multiply 3 by to get 15 is 5, so the thing you perfectly cube to get y to the 15th is y to the 5th, and the thing you multiply 3 by to get 3 is 1, so the thing you perfectly cube to get z cubed is, well, probably no surprise, it's just z. So if you're looking to very explicitly and pointedly write down the things that you perfectly cube to get 125x to the 6th and y to the 15th z cubed, here they are. They're 5x squared and they're y to the 5th and z. So here's where, now that you've picked out the things that are being perfectly cubed, you can kick in the perfect cube factorization setup. So for a difference of cubes, remember this breaks down as a binomial times a trinomial, and the sign on the original sum or difference of cubes carries through as the sign in between the two terms of the binomial. So we've got a minus here, so that minus carries through to the binomial stage here, and the two things that bookend that sign are exactly the two things that are being perfectly cubed to get you the original cube terms in the initial statement of the problem. So those things were 5x squared and y to the 5th z. So the binomial factor in this factorization is 5x squared minus y to the 5th z. And now once you've got the binomial nailed down for either a sum or difference of cubes factorization, remember that the trinomial is always nailed down by applying the same fixed pattern. The first term in the trinomial is the square of the first thing from the binomial. So the square of the first thing in the binomial here would be 25x to the fourth. That's the square of 5x squared. Then the pattern continues with the sign opposite to the sign you have between the two terms in the binomial. So you have a minus there, so now we're going to have a plus. Then the product of the two things in the binomial. So the two things in the binomial are 5x squared and y to the fifth z. So you have their product in the middle. There's 5x squared y to the fifth times z. And then finally, the pattern says you always add on the square of the last thing from the binomial factor. Well, the last thing here was y to the fifth z, so you square that, and you get y to the 10th and z squared. So there it is. There's that pattern. So remember that. That's key for factoring any sum or difference of cubes. The trinomial factor is generated from the stuff you write down initially in the binomial factor by doing square the first thing, opposite sign, product of the two things, plus then the square of the second thing. And then, every time you're done with a particular phase of factorization, as we are here, we've factored the difference of cubes that we started with. You always want to look to see if there's anything else you can do. Well, again, when you look at this binomial factor has no greatest common factors, doesn't have enough terms to be trinomial or grouping, isn't a difference of squares or a sum or difference of cubes anymore, so there's nothing else we can do with that. And remember that the trinomial factor that comes out of a sum or difference of cubes factorization is itself never factorable any further over the real numbers. So with that then, with our unfactorable binomial starting things out and our always unfactorable over the real numbers trinomial wrapping things up, there it is. There's our full factorization for that particular difference of cubes.